Hi, this is Sheikh Rosan Zamir from Institute of Aeronautical Engineering from CSE Department, Section E 23951A059F. Now I am going to discuss about constraint-based object-oriented programming. According to my knowledge, constraint-based object-oriented programming CWOP, is a paradigm that combines the advantages of constraint programming (CP) and object-oriented programming (OOP). CP is a declarative way of solving combinatorial problems by stating the constraints of the feasible solutions. With OOP is an imperative way of modeling the behavior and state of complex systems by using classes and objects. CLOOP always uses to define classes the attributes that can be logical variables and methods that can use constraint to specific the relations between the attributes and the argument CLOOP also supports constraint-based invocation, which is a generalization of the tradition invocation, where dispatch is done based on the types of values of the arguments. CLOOP can be seen as a natural extension of constraint logical programming (CLP), which embeds constraints to into logical programming. Introduction. In this presentation, we will explore the potential of constraint-based object-oriented programming (CBOOP) and its impact on software development. We will delve into principles and applications of CBOOP, uncovering its benefits and challenges. CBOOP is an acronym for Cooperative Business Object-Oriented Programming, a software development paradigm that combines the features of object-oriented programming and cooperative multitasking. CBOO aims to improve the high-level abstraction for concurrent and distributed programming, where objects can communicate and cooperate with each other, message passing, and event handling. Understanding CBOOP. CBOOP is a paradigm that emphasizes constraints and object-oriented programming principles. It leverages constraints to guide the design and behavior of objects, promoting flexibility and maintainability in software systems. Some of the benefits of CBOOP are in support modularity and reusability of code, as objects can be defined and used independently of each other. It facilitates parallelism and scalability, as objects can run concurrently and distribute their workload among multiple processors and or nodes. It simplifies synchronization and coord- coordination, as objects can use logs, semaphores, monitors, or other mechanisms to ensure mutual exclusion and avoid deadlock or race conditions. It enhances fault tolerance and reliability, as objects can handle errors and exceptions locally or delegate them to other objects. Some of the challenges of COO are it requires a high level of abstraction and design, as objects need to be well defined and encapsulated, and their interactions need to be carefully specified and controlled. It may incur a high overhead and complexity, as objects need to manage their own state and behavior and coordinate with other objects through messages and events. Principles of CBOOP. The core principles of CBOOP include encapsulation, inheritance, and constraint satisfaction. These principles enable the creations of robust, adaptable, and efficient software solutions. Applying constraints in CBOOP. Constraints in CBOOP define the rules and relationships among objects guiding their interactions and behavior by applying constraints. Developers can enforce consistency and integrity in the software design. CBOOP stands for Constraint-Based Object-Oriented Programming, which is a paradigm that combines the features of object-oriented programming and constraint programming. Constraint programming is a technique that allows the programmer to specify the desired properties of solution without specifying how to find it. The constraints are then solved by a constraint solver, which can use various algorithms and heuristics to find feasible and optimal solutions. Applying constraint in CBOOP means defining the relationships and restrictions among the objects and their attributes, as well as the goals and preferences of the problem. Benefits of CBOOP. CBOOP offers several benefits including modularity, reusability, and scalability. These advantages contribute to the development of robust and adaptable software systems. Challenges of CBOOP. Despite its benefits, CBOOP presents challenges such as complexity, constraint management, and performance overhead. Overcoming these challenges is crucial for success CBOOP implementations. Real world applications. CBOOP has found applications in diverse domains including finance, healthcare, and manufacturing. Its ability to model complex relationships and constraints it make it valuable for solving real-world problems. CBOOP stands for Component-Based Object-Oriented Programming, which is a programming paradigm that combines the advantages of reusability and high granularity of complex complexity with the features of object-oriented programming, such as inheritance, polymorphism, and encapsulation. CBOOP is a relatively new concept that has not been widely adopted in the software industries yet, but it has some potential applications in the real world. Some of the possible applications of CBOOP are case studies. We will examine case studies showcasing the successful application of CBOOP is solving complex problems and achieving innovation solutions in various concepts of community collaboration and social interaction. CBOOP is often used to develop software systems that are distributed, decentralized, and adaptive. Some case studies that illustrate the use and benefits of CBOOP are the case study of Amul Cooperative in India. This paper examines how to Amul, the dairy cooperative, has adopted a CBOOP approach to design and operate its organization. Amul has a federal structure that allows each unit to be independent and autonomous while also collaborating and sharing resources with other units. Amul has achieved high levels of organizational effectiveness and operational efficiency by using CBOOP. Successive of cooperatives in India. The article showcases some of the successful cooperatives in India that have used CBOOP to create social and economical values. Best practices. To leverage the full potential of CBOOP, it is essential to follow the best practices in constraint modeling, object design, and integration with existing systems. These particles ensure robust and maintaining software solutions. Future trends. The future of CBOOP holds promise and advancements in AI integration, AOT, IoT, and distributed systems. These trends will further enhance the capabilities and relevance of CBOOP in the evolving landscape of software development. Conclusion. In conclusion, CBOOP offers a powerful approach to software development, leveraging constraints to unlock the potential of object-oriented programming. Embracing CBOOP principles and practices can lead to the creation of adaptiveness and real, resilient software solutions. Thank you.